I will wait a couple of minutes and then I will start. Okay, so I'll share my slides now. So this class is the NMR spectroscopy for structural biology. I will be taking 5 classes, 2 hours each, and all the sessions will be recorded and uploaded. So even if you're not in the class, you can see the recordings, and then uh, in the next class, you can discuss any doubts that you have. So the first class will mostly be about the basics of NMR spectroscopy. Now, you know that there is a large spectra of electromagnetic radiations ranging from gamma rays, which have the shortest wavelength, to radio waves, which have much longer wavelengths. And in each of these ranges of electromagnetic radiations are used in different kinds of spectroscopy. Like the gamma rays are used to generate electron and positron from neutrons. X-rays are mostly used for ionization. So if an atom is hit with an X-ray, it will eject an electron and become an ion. UV and IR are used for different spectroscopy. UV is generally for electronic transitions. IR is for rotations or vibrations in the molecule. IR is mostly for molecular vibrations, while microwaves are for molecular rotation. Now it is the radio wave region that is used for this NMR. So this is the region of electromagnetic radiation uh, or radio frequency that NMR uses, which have pretty large wavelengths. And you know that energy is h nu, that is hc by lambda. So larger the wavelength, smaller the energy. So the radio waves do not have much energy, and this is why NMR is a very non-destructive technique. So you can take NMR of a compound without destroying it at all. So you can take NMR once, then you can use it for something else, or you can take NMR under different circumstances. The compound does not get destroyed by NMR since the radio frequency has very low energy. In comparison, while doing X-ray crystallography, X-rays have much higher energy, so sometimes they can destroy the compound. So that is one advantage of NMR over X-ray crystallography or other techniques. Now we will look at the basic principle of NMR. Basically, a nucleus is a charged particle. You know, a nucleus has positive charge, and as it spins, so moving charged particles will have a magnetic field, which will have a magnetic moment. So when there is no external magnetic field, the magnetic moments are shown by this arrow. When there is no external magnetic field, all the magnetic moments are randomly oriented, and so the net magnetic moment capital M is 0. But in the presence of an external magnetic field, you can see these vertical arrows pointing upwards. This is the external magnetic field. In the presence of this field, the individual, you can imagine each nucleus as a small magnet. So in the presence of this external magnetic field, the nuclei will orient themselves either parallel to the field, you can see they are pointing upwards, or anti-parallel, there are some nuclei pointing downwards. So this will lead to a net magnetic moment, which will affect the field that the nucleus is experiencing. So we'll discuss about that later. For now, you can just remember that if we consider this external magnetic field as B0 and the net magnetic moment from the nuclei as M, these two will either add or subtract depending on the direction and give the net magnetic field that is experienced by the nuclei. Now this magnetic moment or mu of a particular nucleus is represented by this formula gamma into I. Gamma is a property of each element known as magnetogyric ratio or gyromagnetic ratio, and you can see gamma has different values for different elements. 1H, which is the most common type of NMR taken, has a gamma value of 42.58 and so on. And I, we will talk about I in the next slide. I is actually the angular momentum. So when you have a spinning particle, a spinning charged particle will have a magnetic moment, but it will also have an angular momentum since it is spinning. And I is a vector quantity, that is why it is represented like this with an arrow on top. This angular momentum vector has a magnitude given by h bar, which you know is the Planck's constant by 2 pi, into root I into I plus 1, where I is a quantum number. Now, I can have different values, which are shown here. Most commonly, the NMR that is done, 1H and 13C, they have I values of half. So the value of this quantum number is fixed for each element, and using this formula h bar root of I into I plus 1, you will get the magnitude of the angular momentum vector. There is another quantum number called magnetic quantum number or small m, and it has values ranging from I to minus I in increments of 1. So suppose your I value is half, then m will be minus half and plus half. If your I value is 1, m will be minus 1, 0 and 1. And so if you have, so the number of m values is 2i plus 1. So now here what is represented by this bold arrow, it is the angular momentum vector I. Now this vector, you can see it will have a z, this is the z axis. If you draw a perpendicular on the z axis, that is the z component of this vector, and it is given by the formula m h bar. So this particular case is where L is actually I here, it is represented by L. So you can consider this is actually I. So I value half means that M can be minus half or plus half. So the Z component can be h bar by 2 or minus h bar by 2. That is these two Z components. And there is a certain angle theta that the vector makes with the Z axis. In order to calculate this theta, So cos theta is base by hypotenuse. So base of this is the z component, that is m h bar. So m h bar divided by hypotenuse is the I vector, that is h bar root I into I plus 1. That is written here. H bars will cancel out. So cos theta is given by this. So if you take cos inverse of this thing, you will get the value of theta. Now another example is where I is 1. If I is 1, the m values are -1, 0, and 1. So this is m0. It's not written here. I'll just write it. m0. So if I is 1, m is -1, 0, and +1. And then the z components will be minus h bar, 0, and plus h bar, because the z components are m h bar. So this is how the angular momentum I is defined. Now there are certain rules for I. In an element, if the atomic number and the mass number are both even, then the nucleus will not have a spin. And if it does not have a spin, the net angular momentum vector will be 0. So an example is 12C6. That is the normal carbon that you have. 13C is a isotope of that carbon, but 12C is the more abundant natural carbon that you have. Here you can see the atomic number 6 is even and the mass number 12 is also even. In that case, this nucleus will not have a spin and the net I will be 0. Now, if you have a mass number odd, like say 13C6. So 13C6 is the heavier isotope of 12C. Here the mass number 13 is odd. Then the nucleus has a half integer spin, like half, 3 by 2 or 5 by 2. 13C has the I value of half. Similarly for 1H, that is hydrogen. Here also the mass number is 1, that is odd, and it has a I value of half. This I value of half is the most common I value that we have in NMR for the because normally in NMR we do 1H or 13C most often. Other elements might have other I values, like suppose the atomic number is odd and the mass number is even. So this case was this second case was mass number is odd. The third case is the atomic number being odd. For example, deuterium, that is the heavier isotope of hydrogen. You can see the atomic number is 1, that is odd, and mass number is 2, that is even. In that case, the nucleus will have an integer spin, that is I value can be 1 or 2 or 3. In case of deuterium, it is 1. So, what is important to remember here is that nuclei with even atomic mass and even atomic number, they have I0. So I0 means there is no spin. So there will be no magnetic moment. And if there is no magnetic moment, they will not absorb radio waves and they will not be detectable by NMR. So these are called NMR inactive nuclei. Whereas in the other two cases, the nuclei will be detectable by NMR and they are called NMR active nuclei. You can see another example is O16 with atomic number 8. Both are even. So you can see number of spin states, everything is 0. This will not be detectable by NMR. Now, what is interesting is that in the absence of a magnetic field, all the spin states will have the same energy. But when you have an applied magnetic field shown by E here in the upwards direction, then the spin states will split up into different energies. So we know the nucleus is a charged particle which is moving, and any moving charged particle will have its own magnetic field. Now in the presence of this magnetic field, E shown here in the upwards direction, each nucleus will align itself either in the same direction of the field. You can see E is upwards, or you can see here, the applied magnetic field is upwards. So the nucleus can orient itself upwards in the same direction as the field or downwards, that is in the opposite direction of the field. these two cases will have different energies. When it is in the same direction of the field, it has lower energy, and the opposite direction will have higher energy. So how do we know that? Energy is defined as the dot product of the magnetic moment into B0, that is the applied field, with a negative charge added. And we know that the magnetic moment can be written as gamma Iz. So this, we are only considering magnetic moment in the Z direction, since the applied field is also in the Z direction. So the magnetic field is gamma Iz. Gamma is the gyromagnetic ratio, Iz is the angular momentum in the Z direction. So we can write Iz as m h bar. So the magnetic moment mu can be written as gamma m h bar. So now if we put this value of mu in the equation of the energy, so we know, so this example shown here is for I equals half. We know if I equals half, m can be plus half or m can be minus half. So with these two values of m, if we put in the equation of E, we can see that when m is plus half, then this minus sign will come and the net energy will become minus gamma m h bar B0. Minus half, since m is half. So minus half gamma m h bar B0, which is what is written here. And this will be in the same direction as the E, that is the applied magnetic field. And the other energy level, where m is minus half, this minus sign and this minus sign will cancel out, and the net energy will become half gamma h bar B0, which is the higher energy level. So between these two energy levels, you can see the magnitude is same, but the negative definitely has lowered energy. And we often call this alpha and beta. Now, you can see that when you have two energy levels, the lower level and the upper level, there is a Boltzmann distribution between them. And this means that the number of nuclei in the upper level divided by the number of nuclei in the lower level, this ratio can be given by E to the power minus delta E, that is the energy difference between the two levels, by kT. And we are writing delta E as h nu. So E to the power minus h nu by kT. We know h and k, they are constants. T is the absolute temperature. And using this, we can find out that what is the ratio of number of nuclei in the upper level by the lower level. So generally, suppose you have n nuclei in the upper level and the lower level has slightly higher number of nuclei. Here it is shown as 9. So the lower level has 9 extra nuclei. Now it is because of this 9 nuclei that the NMR signal is being seen. Because otherwise, if they have equal populations, NMR is normally seen because by absorbing energy, the nuclei is getting promoted, and that absorbed energy is observed in the NMR spectrum. Now, if they have equal populations, there will be no transitions from lower or upper level, and so there will be no signal. So the signal is due to this 9 extra nuclei. And so more the difference between the upper and lower energy levels, greater will be the NMR signal intensity. Now, that is what is shown here, that again you have the two levels splitting up, alpha and beta, with their respective energies. And the difference in energy between these two levels, delta E, if you subtract this energy by this energy, you will get gamma h bar B0. You can write gamma B0 as omega naught. What is this omega naught? This is something called the Larmor frequency. So what happens is that when you have a angular momentum, you can see this vector, this arrow here, it spins. So the angular momentum vector, it does not stay pointed in one direction. One moment it is here, one moment it will come here, one moment it will come here, so on. it will spin in this kind of a conical fashion, and the frequency of this spinning is termed as, so this kind of a movement is called as Larmor precession, and the frequency of this spinning is called omega 0 or Larmor frequency, and it is defined as minus gamma h naught. So here the delta E is gamma h bar B0, and you can write B0 and H0 is basically same, that is the applied field. You can write gamma B0 as minus omega naught. So delta E is minus omega naught h bar. So that is how you can define this energy difference in terms of this Larmor frequency. Now, one thing is that when you have many different nuclei, this vector can be oriented in many different directions. So here is a example shown where you have this kind of a conical structure, and the angular momentum vector of different nuclei are oriented in different directions. Now, if you take the xy component of each of these vectors, so suppose you have one vector here, the x component is here, y component is here. Then another vector might have x component in the opposite direction, y component in the opposite direction. So they will cancel out. Like this, if you take the xy component of each of these different vectors, they will all cancel out because they will be in opposite direction. So the xy component becomes 0. So the net magnetization is along the z axis, and this is why we mostly consider the net magnetization being along the z-axis. And this kind of a random orientation of the angular momentum vector, which leads to cancelling out of the spins, this is called the hypothesis of random phases. So now we have looked at the Boltzmann distribution, where the ratio of the number of molecules occupying the upper level by the lower level is e to the power minus delta E by kT, where delta E is the energy difference between the two levels, which can be written as h nu. We have seen in the previous slide that delta E can also be written as minus omega naught h bar. So here, we are using this. So delta E can be written as gamma h bar B naught. So you have written the e to the power minus, instead of delta E, gamma h bar B naught by kT. Now, if suppose you are applying some external energy, you are applying an external radio frequency, say h nu, and this is promoting some electrons to the upper level, and the populations are changing. So when this is happening, some nuclei from the lower level are going to the upper level. After that, they have to return to the lower level, so they have to release the energy. So where will this energy released go? Normally, it is released into the lattice. So lattice is basically everything other than the nucleus you are studying. Now, nuclei are not found in isolation. They are inside an atom. There may be other atoms surrounding it. It may be part of a crystal lattice, or it may be in solution. So everything around the nucleus is the lattice. So any energy released is absorbed by the lattice, or if suppose some energy is needed to be promoted, that also it gains it from the lattice. So this kind of phenomena is called spin lattice relaxation or coupling, where suppose there is a population adjustment happening. Some nuclei are going to the upper level, so they have to absorb energy. They are absorbing it from the lattice. Or some nuclei have to come down to the lower level, so they are giving out energy. That extra energy is also absorbed by the lattice. So any kind of population adjustment like this is called as spin lattice relaxation or coupling. Spin lattice relaxation is characterized by a time constant called the spin lattice relaxation time T1, also known as longitudinal relaxation. So you have the two energy levels split up, alpha and beta, and the population of the lower level is N alpha, population of the upper level is N beta. So the population difference at any time t, we are representing by n, is n alpha minus n beta. So if we consider the population difference at equilibrium, we are just writing it as n0 is the population of alpha at equilibrium minus the population of beta at equilibrium. So the population at any time, population difference at any time t, that is n, can be written as the population difference at equilibrium n0 into 1 minus e to the power minus t, that is the time, divided by t1, that is the spin lattice relaxation time. So if this time is infinite, that is if you give infinite time to the system, then eventually n will become n0. So in order to reach equilibrium, the system actually takes infinite time. Now, when this nuclei is going from the lower level to the upper level, I just discussed, it has to absorb some energy h nu. So h nu is given to the system, and this spin, which was aligned with the magnetic field in the lower energy level, goes to the upper energy level, where the spin is now in the opposite direction of the magnetic field. This energy absorption is a quantized process. It can only absorb that much energy, that is the energy difference between the two levels. And this is known as resonance absorption energy. And this energy absorbed is in the radio frequency region. So we started this lecture by talking about in which region of the electromagnetic radiation the NMR works. And since this energy absorbed is in the radio frequency region, that is where we see the NMR. So generally, any radio frequency pulse can be written as 2h1 cos omega t. Suppose you have a radio frequency pulse like this. Sorry, just ignore this. Suppose you have a radio frequency pulse like this. Then the radio it can be written as 2h1. h1 is this amplitude, cos omega t. Omega is the frequency. So using that, the radio frequency pulse is represented that you are supplying in order to promote the nucleus to a higher level. So now, what happens in NMR is that we saw that the x and y axis components get cancelled out. So the magnetization is in the z direction. Now, a radio frequency or RF pulse is applied, which is shown by B1 here, to this magnetization. This orients the magnetization into the XY plane. So the XY magnetization was initially 0. We have created XY magnetization by bringing the it from Z axis to the XY plane. This is called transverse magnetization. Now, when the RF pulse is switched off, then the system will try to go back to its original equilibrium condition. So you can see this is the Z component, XY component. XY component was initially this much. After some time, it will become lesser, then it will become lesser. So the XY component is reducing and the Z component is increasing till it regains the original Z component. So this happens in this kind of a spiral way. And once the initial Z component is restored, then you will not see the NMR signal anymore, because the NMR detector is actually placed in the XY plane. So as long as there is a signal in the XY plane, the detector will be able to pick it up and you will see the NMR spectra. But once it is fully back in the Z axis, the XY component is 0, the NMR spectra will disappear. So this kind of a process where you have supplying an external magnetic field, you have brought, so the initial magnetization, one second. Initial magnetization was in this direction. By supplying an external field, you have brought the magnetization to the XY plane. Now, as time goes on, you can see this axis is time. As time goes on, the XY component shown by the red arrow is decreasing and the Z component shown by the green arrow is increasing. So the signal, since the signal depends on the XY component, the signal has highest intensity at the beginning, and at the end, when the XY component is 0, the signal also becomes 0. So this decay of the signal is characterized by a time constant known as the spin-spin relaxation time, or T2. So if you imagine the initial signal, just one second. So if you imagine the initial signal where the entire component was in the XY direction, if you imagine it, this is the highest signal. And as the XY component is decaying, the signal also decays. Till at a point, the signal completely becomes 0. So this is the entire process by which the spin is relaxing. Now, what kind of transitions are allowed? When we had I as half, there were only two energy levels, minus half and plus half. So there was only one possible transition. But if suppose I is 1, then M is minus I to plus I. So M will be minus 1, 0 and 1. Now, the rule of transitions, or the selection rule, says that delta M can be plus minus 1. So you can go from plus 1 to 0 or vice versa. You can go from 0 to minus 1 or vice versa. But plus 1 to minus 1 is not allowed since delta M becomes 2. So this is called single quantum transitions, where M can only change by plus minus 1. Now you will see that so when there are two energy levels, there is a particular when such a transition is happening, suppose it's coming down from the upper to the lower level, and energy is released at h nu, which you can write, suppose h nu can be written as hc by lambda. So this is one particular wavelength. So the spectra should be a single line like this at a particular wavelength. But the actual spectra seen has a certain width, which we are saying line width. So this is called spectral line broadening. And why does this happen? This is because of Heisenberg's uncertainty principle. So energy is not a single level like this, but there is a range of levels. You can see there is a range of levels. So there is a certain uncertainty in the energy, which we are calling as delta E. So if delta E is the uncertainty in energy and delta T is the lifetime in that state, then one form of the Heisenberg's uncertainty principle is delta E into delta T will be approximately h bar, that is h by 2 pi. So since there is this uncertainty in energy, this won't be a single wavelength. It will be a range of wavelengths. Suppose, so you can see instead of a single wavelength, it is a range of wavelengths. And that is one of the reasons behind this line broadening. Another reason of line broadening is that suppose this is the NMR tube. There are different molecules in different regions of the tube. Now, so far we have considered an ideal case where a uniform external magnetic field is supplied, H0. But in reality, what happens if suppose your NMR spectrometer is not good enough, the external magnetic field is inhomogeneous. It will have different values in different regions. And so each of the different nuclei is experiencing a different magnetic field. And this also causes a line broadening. And this is due to field inhomogeneity. So these are the two factors that affect the broadening of lines in a spectrum. Now we will go into some properties of NMR. Now suppose you have a nuclei that is surrounded by very less electrons. So basically, I'll discuss this. So this nucleus is shielded by different electrons that surround them. When you are applying a magnetic field, these electrons are circulating. So you have applied a magnet. You can see the plus sign shown here is the nuclei in the middle, and the cloud shown here are the surrounding electrons. When you're applying a magnetic field, the electrons will start to circulate, and we know that the direction of this will be in the opposite direction to the magnetic field. So if the applied magnetic field is upwards, this induced magnetic field, you can see this middle arrow, the induced magnetic field is downwards. So if that is the case, the nuclei will experience a net magnetic field. So the nucleus will experience a net magnetic field of B0 minus Bi, because it is experiencing B0 in the upwards direction, this B0, and B induced, I'm calling it Bi, in the downwards direction. So this will be the net magnetic field experienced by the nucleus. You can also write it as H. So H0 and Hi. And so this is how, so when you have very few nuclei surrounding when you have very few electrons surrounding the nucleus, then the induced current is low. So the Bi is low. So nucleus is experiencing a stronger magnetic field. And when you have a large number of electrons surrounding the nuclei, then the induced current, or Bi, is very large. So nucleus will experience a weak magnetic field. As a result of this, each proton in the molecule, even though you're applying a uniform magnetic field B0, each proton in the molecule is experiencing a different magnetic field due to the different chemical environment. And so that will help you distinguish between different nucleus in the molecule. So there is this formula, H induced is H0 into 1 minus sigma I. Sigma I is called the screening constant. That is how much the nucleus is being screened by the electrons. So in this system where there are less electrons, sigma I is low. If sigma I is low, one second. Sorry, Hi is not induced magnetic field. Hi is actually the effective magnetic field. I'll write it like He, so there is no confusion. So He is the net magnetic field that is being, so the effective magnetic field is H0, 1 minus sigma I. When there are less electrons around the nucleus, the screening is less. Sigma I is less, and so it is affecting, He is greater. It is experiencing a stronger magnetic field. And when there are a large number of electrons surrounding the nucleus, sigma I is large, which makes He small, and it is affecting, experiencing a weaker magnetic field. So the sigma I will give us an idea about the electron density around the nucleus. So it will give us an idea of the structure as well. So this is the very basic principle of how NMR helps us understand the structure. Now I will define a term called chemical shift, or delta I, which is defined as HR minus HI divided by HR into 10 to the power 6. So this is in terms of the magnetic field. We generally do not use this. What we use is that, so let me first explain the terms. When we take NMR of any compound, we add a certain reference to it. So why are we adding the reference? Because if you see the NMR spectra, reference is something we want at 0, so that we can compare that how much the molecule is shifted compared to the reference. So HR is for the reference, HI is for the nucleus we are observing. So this is the formula in terms of the magnetic field. The more common way to write it is in terms of the frequency. So in the numerator, you have the frequency of the nucleus we are observing minus the frequency of the reference divided by mu 0, that is the spectrometer frequency, that is in megahertz. And we multiply it by 10 to the power 6 because the unit of delta is ppm, that is parts per million. So about this reference, the most common reference used is tetramethylsilane or TMS, that is silicon attached to 4 methyl groups. So why is this used as a reference? Firstly, it is non-toxic, so it is safe to use. Next, it is inert, so it will not react with the compound you are analyzing. It also has a low boiling point, so you can remove it from the compound, distill it, and use it again. And all these hydrogen atoms, so 3 into 4, 12 hydrogen atoms, are chemically all equivalent, and you will get a single peak. You can see TMS is showing a single peak. Also, since there are 12 hydrogen atoms, it will be a very intense peak. You do not need to use much of the reference. And since basically silicon is more electropositive than carbon, so the electron density of silicon will move towards the methyl groups. So these methyl groups are actually very shielded. Hence, since they are very shielded, they will appear far away from other molecules that you are analyzing. So there will be no confusion between which is your reference signal and which is your molecule signal. Since it is the reference, we generally assign it the chemical shift of 0, and the position of other signals are measured relative to this. Now, about chemical shifts. So this delta is termed as the chemical shift. Now, we will look at different chemical shifts of different molecules. So basically, what happens is that more the electron density around the molecule, less will be the chemical shift. In TMS, we saw that the hydrogens have a lot of electron density around them since they are pulling it from silicon. So this hydrogen is kind of like this case. And in that case, the delta is 0. Now, as the electron density around the hydrogen decreases, it becomes like this. The delta value increases more and more towards this side. So we will look at, suppose we have CH3X, where the X is varied from fluorine to OH to chlorine, bromine, iodine, and finally hydrogen. So depending on the electronegativity. So suppose I have CH3X. X will withdraw electron density towards itself. So this hydrogen will get a delta plus charge. Greater the electronegativity of X, delta plus will be greater. And with greater delta plus, this chemical shift will also be greater. So fluorine has the highest electronegativity of 4, and it decreases towards this side. So with highest electronegativity, the positive charge on hydrogen is highest, and so this chemical shift will be highest. You can see in CH3F, chemical shift is 4.26, and slowly as electronegativity decreases, the chemical shift also decreases, till when it is CH4, that is least electronegativity difference between hydrogen and X. Then, so X is technically another hydrogen here. So in that case, chemical shift is the lowest. It is closest to TMS because there is no electron density pull towards X, since X is also hydrogen and you are observing other hydrogens. Now, if we look at the substitution effects. So suppose you have CHCl3 with 3 chlorine groups attached. Suppose so if you have 3 chlorine groups attached, all 3 will pull electron density towards itself. This hydrogen will get a positive charge. This will have the highest chemical shift. If there are 2 chlorines, chemical shift will be lower. 1 chlorine, it will be even lower, and so on. Now, what about distance? Here, the hydrogen you are observing, bromine is also directly attached to that carbon. Here, bromine is attached 1 carbon away. Here, it is attached 2 carbons away. So greater the distance of the electronegative element from the hydrogen you are observing, more the distance is increasing, less it will be its effect. So chemical shift is also decreasing. So multiple substituents have stronger effect than single substituents, and shorter the distance of the substituent from the hydrogen you are observing, greater will be its effect. Another factor that we have to look into is hybridization. Now, we know that different kinds of hybridization can be there, like sp, sp2 or sp3. And we know that as the S character increases, electronegativity also increases. Here you're looking at a hydrogen attached to a sp hybridized carbon. This is the most electronegative carbon compared to sp2 or sp3. And so this hydrogen will have the greatest positive charge and the highest chemical shift. As you go, so that is what it was supposed to be. However, when you look at sp2, sp2 has lower electronegativity. So chemical shift should be lower, but it is actually higher. So there is some anomalous effect that is occurring that we will discuss in the coming slides. But you can see clearly that compared to sp3, which has the least electronegativity, sp2 and sp, they are both more electronegative. So they will both withdraw more electron density towards themselves, making the hydrogens more positive and increasing chemical shift. So compared to sp3, the trend can be understood. But between sp and sp2, there is an anomaly if we only consider hybridization. Because according to hybridization, sp should have the highest chemical shift. But that is not what happens. So what is this additional effect? This is something called anisotropy. Now suppose you have a double bond or an aromatic ring. Now when you apply a magnetic field, suppose in the upwards direction, the electrons in the aromatic ring will circulate and they will have an induced magnetic field in the opposite direction to the applied magnetic field. So the applied magnetic field is upwards, the induced magnetic field is downwards. Similarly, for the double bonded alkene, applied magnetic field is upwards, induced magnetic field is downwards. What this will do, it is downwards here, but when you complete the entire magnetic ring, you can see that the hydrogen that is attached to the aromatic ring or to the double bonded carbon, that hydrogen is experiencing the induced magnetic field in the upward direction. So this hydrogen is experiencing a net field B0, that is the applied magnetic field, plus Bi, that is the induced magnetic field. Sorry, 1 second. So this hydrogen is experiencing the applied magnetic field B0 plus the induced magnetic field shown in blue Bi. It is experiencing a higher magnetic field. That means higher magnetic field, we have seen that stronger magnetic field means that it will be more de-shielded. So stronger magnetic field means there are less electrons around it, and less electrons means it is more downfield shifted or de-shielded. So this hydrogen attached to the aromatic ring will have greater values of the chemical shift. Similarly, for the hydrogen attached to the double bonded carbon of the alkene, it is also experiencing a net field B0, the applied field, plus Bi, the induced field. So it is experiencing a net greater field, and so it will be more downfield shifted. This can explain this anomaly. So one of the factors that explain this anomaly is that this hydrogen is attached to a double bonded carbon. Other than the hybridization effect, this kind of ring current effect, or you can call it ring current in case of aromatic compounds because there's a ring, or in case of the double bonded, you can call it the anisotropic effect. So additional downfield shifting will happen due to this, which overwhelms the effects from hybridization, and that is why the hydrogen attached to the double bond has greater chemical shifts. Now, here are some examples. So this is an aromatic ring. These are the hydrogens that are in the plane of the ring. And then there is a certain connection, and this middle hydrogen actually appears around the middle of the ring. So what we saw in the previous slide, we saw the applied magnetic field in the upward direction. And if we consider this the induced magnetic field, it is downwards here and up. So this hydrogen, it is experiencing the induced magnetic field downwards, applied magnetic field upwards. So it is experiencing B0, which is this one, minus Bi, which is this induced magnetic field downwards. They are in opposite directions. So if that is the case, then the chemical shift will be much lower. In fact, it goes to negative values, -1 ppm, which is called being shielded. Whereas if you look at this hydrogen, which is in the same plane as the ring, here induced is in the upward direction, applied is in the upward direction. So chemical shift delta values will be much higher. It is 2 ppm. Similarly, if you look at this aromatic system, the inner hydrogens will have lower chemical shifts. They are negative actually, -1.8 ppm. Whereas the outer hydrogens, they will experience this kind of summation of fields. So the chemical shift is so much greater, 8.9 ppm. And similarly, these are some other examples. So any hydrogen which falls along the axis of this aromatic ring. So suppose this is the middle part of any hydrogen which falls along this, they will have lower chemical shifts. You can see this one has -1.4 ppm. Whereas any hydrogens in the same plane as the aromatic ring will have greater chemical shifts. We looked at the double bond. Now let's look at the triple bond. In the triple bond, so here it is, so this is actually the triple bond, C triple bond C, C triple bond C, and the hydrogens are linear. So here what happens when you apply an external field B0, the rotation of the electrons happen in this direction that is shown by this arrow. And when that is happening, along this axis of the molecule, the induced magnetic field is in the opposite direction. So along this axis, the induced magnetic field is downwards. So this hydrogen will experience a net field of B0, that is the external field, minus Bi, that is the induced field. So the hydrogen attached to the triple bonded carbon is actually quite shielded. So again, if we look at the double bonded alkene, then in perpendicular to the plane of the alkene, the hydrogen will be shielded, and in the plane of the alkene, the hydrogen will be de-shielded. That is, the chemical shift will be higher. And it is the opposite in case of the triple bond, where along the axis of the triple bond, the hydrogens are shielded, chemical shift is lower, and perpendicular to the axis, the chemical shift will be higher. So that is about the triple bonds. Now we will discuss some sample questions. Here the first question is that which of the nuclei given below has no magnetic moment? I'll just give you 1 minute to think about it, and then I'll discuss the answers. So the answer is actually deuterium, because if you remember the rules, for any element, we have to look at the mass number and the atomic number. When sorry, the answer is C, that is 12 carbon. So for any element, when we look at the mass number and atomic number, if both are even, it is NMR inactive. In case of the carbon, the atomic number is 6, nitrogen atomic number is 7, deuterium is 1, and hydrogen is 1. So you need both mass and atomic number to be even for it to be NMR inactive, that is, it will have no magnetic moment. So in hydrogen, both are odd. In deuterium, atomic number is odd. In nitrogen, again, both are odd. Only in this case, both are even. So it has no magnetic moment. So the correct answer is C. The next question is asking a proton in a magnetic field of 10 Tesla equals to how many megahertz? So here the formula to remember is that frequency nu is gamma B0. You can memorize the gamma values for the two common nuclei, 1H and 13C. For 1H, it is around 42.58. So you put the value of 42.58 and the unit of gamma is megahertz by Tesla. Into B0, the applied magnetic field, the question is saying it is 10 Tesla. That will give you 425.8 megahertz, which is around 420 megahertz. That is option C. So to solve questions like this, you have to remember the value of the gyromagnetic ratio. You can just remember it for 1H and 13C, which are the most commonly used nuclei in NMR. The next question is asking, if a proton absorbs energy at 500 megahertz, then approximately at which frequency the nitrogen will absorb? So here, what you have to remember is that you know that the energy, when in the presence of an external magnetic field, it splits up into two levels of different energies. And we know the difference in energy between these levels, delta E, is gamma h bar B0. So since B0 is constant, we are in any NMR experiment, you can consider the external magnetic field as constant. And here it is given as 500 megahertz. So if you take the, and we know delta E is written as gamma h bar B0, it can also be written as h nu. So if you divide this equation for nitrogen by hydrogen, B0 is constant, it will cancel out. The constants h bar and h will cancel out. So you will get frequency of nitrogen by frequency of hydrogen is the gyromagnetic ratio of nitrogen by the gyromagnetic ratio of hydrogen. So if you look at the gyromagnetic ratios, you can see that for nitrogen, so for nitrogen, we consider 15N generally. Like if nothing is mentioned, you consider 15N. So for nitrogen, it is around 4. For hydrogen, it is around 40. So hydrogen has 10 times greater gynomagnetic ratio. So when you take nitrogen by hydrogen, you get 0.1. So the frequency of nitrogen is 0.1 times the frequency of hydrogen. And we have been told the frequency of hydrogen is 500 megahertz. So 0.1 into 500, nitrogen will be around 50 megahertz. That is option D. So here again, you don't have to memorize the exact gynomagnetic ratio. You can just remember that compared to 15N, 1H has 10 times the gynomagnetic ratio. The next question is asking, which is the more sensitive nucleus among the following given examples? So here the thing to remember is that sensitivity depends upon the natural abundance. So among these examples, deuterium has a natural abundance of only 0.015. 13C is also very low, around 1%. And 15N is also only 0.37%. So 31P, that is phosphorus, that is the only isotope of phosphorus. So 100% of phosphorus exists in that isotope. So what does that mean? That means suppose you are doing 13C NMR and you take any compound, then 99 of the nuclei will be 12C, that is NMR inactive. Only one nucleus will be 13C since the abundance is 1%. And it is from that nucleus you will get the NMR signal. So it is not a very sensitive method because you will need a lot of compound. Otherwise, if you have very less sample, the signal will be very weak. Whereas for 31P, 100% of the nuclei exist in the NMR active form, that is 31P. And so even if you take a very small amount of the sample, you will get a good signal. So that makes it a very sensitive nuclei. This again, you don't have to remember the exact abundances. You can just remember there are certain nuclei like 19F and 31P which have 100% abundance. That is, there is only one isotope, which is the NMR active isotope, and they are very sensitive nuclei. Among the commonly used NMRs, 1H NMR is very sensitive because 99.9% is 1H, that is the NMR active nuclei. Another question is asking that NMR spectra of pure ethanol will have how many peaks? So the answer is, we will first look at the structure of ethanol. Ethanol is CH3CH2OH. So you have three different kinds of hydrogens. One that is directly attached to O, one in the CH2 which is attached to the OH, and one is the CH3 which is further away from the OH. So you will have three peaks because there are three different kinds of hydrogens. This question is asking, NMR spectrometer provides dash and dash methods of determining structure in soluble chemical compounds. So here the answer is accurate and non-destructive. So NMR spectra is very accurate and it is non-destructive because we have seen that NMR spectra uses radio frequency and radio frequency has very low energy. So I started the class itself by saying that in NMR spectra, the sample is not destroyed. It can be used again and again. So NMR spectra is accurate and non-destructive method of determining structure in soluble chemical compounds. We will now come to the next part. Just give me some time. I'll start the next part in just some time. Right. So I'll continue with the next few slides. Just 1 second. So we have seen that when you have a nucleus and it is surrounded by a lot of electrons, then the nucleus will experience a net field, that is the external magnetic field B0 minus the induced magnetic field, which is in the opposite direction, which is written here as sigma B0. Sigma is the screening constant. And larger the screening constant, this value becomes lesser. And so, larger the screening constant, more the nucleus is shielded, and so more lower the chemical shift. Now, chemical shift delta is defined as nu I minus nu R by nu 0, where nu I is the frequency of the nucleus we are observing, nu R is for the reference, which normally we add TMS, and nu 0 is the spectrometer frequency. And this is just a recap of what we have seen so far. So TMS, we consider it having a chemical shift of 0 and more. So when the electron density around the nucleus becomes lesser, it becomes more downfield shifted or deshielded. And if it is like this, where the nucleus is very much surrounded by electron density, then it will be upfield shifted or shielded. Here an example is shown of a compound having a double bond. So there are three different kinds of hydrogens here. HB, which is directly connected to the carbon attached to the electronegative element chlorine, and HA and HC. Now, why these are different? Because they cannot interconvert into each other due to the double bond. The double bond cannot rotate freely. So HC is cis to the chlorine and HA is trans to the chlorine, and so they have different chemical environments, and this compound will show three peaks in the NMR spectra. Definitely HB will be most downfield shifted since it is closest to the electronegative chlorine. Now between HC and HA, what happens is that chlorine withdraws a lot of electron density towards itself. And so there is a large electron cloud surrounding chlorine. And so HC gets shielded to some extent due to this electron cloud. And so HC is upfield shifted compared to HA. This is just an example of what we have seen so far. Now there are two methods that are generally used while recording NMR. One is the internal standard method. Here in the same tube, you take the sample you want to analyze and the reference, and you take the spectra together. So this is what we have seen so far, that is the TMS. TMS is added to the sample, spectra is taken together. TMS is generally considered 0, and compared to that, the chemical shift of the sample is calculated. The other method is called external standard method. Here you separately take the NMR of the sample you want to analyze and the NMR of the reference. This is called an external reference because it is not mixed in with the sample. Then these two spectra are combined and a different spectra is taken to get the chemical shift of the sample. So these are the two general methods that are used. This is the more commonly used method, which is the internal standard method, since you have to record just one NMR in this method. So for the 1H chemical shifts, basically the range is from around 0 to 12 or 13, and different kinds of protons appear in different regions of the spectra. So the saturated protons, that is sp3 hybridized protons, they are the most upfield shifted. Then you have the allylic protons. The protons with electronegative elements appear around 2.5 to 4.5. And as the electronegativity of the element is higher, it gets more downfield shifted. Then you have the vinylic protons, that is protons that is attached to double bond, or aromatic protons, that is proton attached to an aromatic ring. We know that for double bond or the protons attached to aromatic ring, there is an additional effect known as ring current effect or anisotropic effect that makes them more downfield shifted. And that is why they appear around this range. And then you have the RCHO, that is aldehyde. Aldehyde is so you can consider, we saw that with C double bonded C, if there was a hydrogen, this was already downfield shifted around here, 4.5 to say 6.5. Now there is an additional electron withdrawing effect of oxygen. So this will be even more downfield shifted around 10, that is the aldehyde. And finally, you have the carboxylic acid, which is RCOOH. Carboxylic acid, basically, there is additional hydrogen bonding. So if you have two molecules of carboxylic acid, hydrogen of one molecule can form hydrogen bonds with this carbonyl oxygen of the other molecule. So what will happen whenever there is hydrogen bonding? More electron density will be withdrawn away from the hydrogen. So this delta plus charge on the hydrogen will increase even further. That is why carboxylic acids are very much downfield shifted up to even 12 ppm. Now 13C chemical shifts have a much greater range. 1H was from 0 to around 12. 13C can go up to 200 or even more. Again, different regions of the spectra are assigned to different groups. And if you remember these ranges, then from a spectra you can predict, looking at the peak of the spectra, you can predict that this peak is belonging to an aromatic carbon or aldehyde and so on. So different functional groups appear in different regions of the NMR spectrum. Now we will discuss a concept called spin-spin coupling. Here you have two hydrogens which are separated by 3 bonds. So it is 1, 2, 3 bonds. HA and HB separated by 3 bonds. There are two interactions possible between this. One is dipolar interactions, which we will discuss later. The more common type of interactions that is observed in solution state NMR is called spin-spin coupling or J coupling. What happens is that when you have a single proton, it has two energy levels, plus half and minus half. Now, when this proton is coupling with HB, then each level splits up into two more levels. So initially you have two levels, lower one is called alpha, upper one is called beta. Now you have this, just one second. Now the lower level is, so this is suppose for the HA. Now HA is getting split up into two more levels. Again, they have been called as, so alpha is, so HA will have its own alpha beta, HB will also have alpha beta. So each level will split up into two more levels. So when you have two protons coupling with each other, there will be a total of 4 energy levels. And we know that the allowed, so how will you calculate? So here M was plus half and minus half. Now when we have energy levels like this, how will you calculate M? The M of each level is summed up to get the M of these combined energy levels. So alpha is combining with beta. Alpha M is half, beta M is minus half. So total M of this lowermost level is 0. Then you have alpha with alpha. So plus half, 1. Then beta with alpha, again plus half minus half becomes 0. And beta with beta, that will be minus 1. So this is the M. The same rule applies, that is only single quantum transitions are allowed. So M can change by plus minus 1. So the allowed transitions are from, so let me just write out the states. This state is alpha beta. This state is alpha alpha. This state is beta alpha. This state is beta beta. So alpha beta to beta beta. So it's going from 0 to minus 1. That is allowed, shown by this blue arrow. Or alpha alpha to beta alpha, 1 to 0. That is also allowed. But you cannot go from 0 to 0, like alpha beta to beta alpha, both are 0. You cannot do that, because then delta M is not changing at all, and that is not allowed. So the same selection rules still apply. Now, how? So there are two transitions that are allowed when only, so instead of one peak, here you are observing one peak. Here, when there were only two energy levels, you are observing one peak. Now, since there are two allowed transitions, you will observe two peaks. These are the two allowed transitions. So A will split up into two peaks. Similarly, B will be split up by A into two peaks. And the difference in chemical shift between these two peaks is called the J coupling constants, and they are equal whether A is split by B or B is split by A. So this is how spin-spin coupling happens. Now, suppose this is a 3-bond coupling that we discussed, separated by 3 bonds. This can happen 3 to 15 hertz. So this difference can be from 3 to 15 hertz. Now, if it is 2 bond, suppose 2 hydrogens connected to the same carbon, that is 2 bond. Then it is in the range 14 to 18 hertz. You can also have 1J coupling, like 13, like carbon directly attached to hydrogen, or nitrogen directly attached to hydrogen. So the carbon is 13C, which is NMR active. It is splitting the hydrogen, or the 15N NMR active nitrogen is splitting the hydrogen. They will have different values of this coupling constant. So this was coupling between two spins. When there are two spins, the single line will split into two lines. Suppose you have 3 spins. They can be arranged in 3 ways, either linear like AMX linear, or triangular like AMX. Now if it is linear, A is split by M. So it will be like one peak is splitting up into 2. Coupling constant, we are calling it as JAM, since A is being split by M. And this is a doublet because there are 2 peaks. Now M, it will be split by both A and X. First, it will be split by A into 2 peaks with the coupling constant being JAM. And then each of this peak will be split into 2 by the X. So this is splitting into 2, and again this is splitting into 2. Here the coupling constant is JMX. So from one peak, you are now getting 4 peaks, and we call it doublet of doublet. because initially there is a doublet and again there is a doublet. And similarly, X will be split by M into a doublet with the coupling constant Jmx. Now, if you have a triangular system, each of them are being split by the other two. So each of them will give a doublet into doublet. So this is how the spin-spin coupling happens between three spins. And again, you can, so each of the spins can have alpha beta, and you can have different combinations of alpha beta, and you can add up the M of each to get the total M and apply the selection rule, that is delta M plus minus 1, into whether the transition is allowed. Like suppose alpha alpha beta, the total M is minus half. Total M of alpha alpha beta is minus half. Because alpha is half, minus half, beta is plus half, they are getting cancelled out. Plus half. So alpha and beta M is getting cancelled out, and one alpha is plus half. Then alpha beta beta, again one alpha and beta will cancel out and you will have minus half. So this transition is allowed because M is changing by 1. But if you look at, suppose beta alpha beta, again here alpha beta is getting cancelled out, beta will have minus half. So again this is also allowed. But if you look at, say, so similarly you can do for each and find out which transitions are allowed. So we have looked at the chemical shifts, we have looked at the coupling constants. Another factor is the intensity ratio. So ethanol, CH3CH2OH. We saw that it will have 3 peaks because there are 3 kinds of hydrogen. Now, what about the intensity ratio? The OH hydrogen is only 1. CH2, there are 2 hydrogens, and CH3, there are 3 hydrogens. So the intensity ratio will be 1 for the OH, 2 for the CH2, and 3 for the CH3. So that is how the number of protons can also be predicted from NMR. And if we look at the coupling, the general rule of coupling is that if there are 2 neighboring protons, it will be split, if there are n neighboring, so it is called the n plus 1 rule. So CH3 has 2 neighboring protons, so it will have 2 plus 1, 3 peaks. CH3, you can see 1, 2, 3, it is splitting into 3 peaks. CH2, now the important thing to remember is OH is an exchangeable proton. Suppose ethanol dissolved in D2O. This OH can exchange with D2O, so it will not participate in coupling. So CH2 has 3 neighboring protons and 3 plus 1 is 4. So CH2 peak is divided into 4 smaller peaks. And since OH is exchangeable, it will not have any coupling. It is appearing as a single peak. Now, we will look, the kind of NMR we have seen so far is called continuous wave NMR. And why is that? So when you have an energy level in the presence of a magnetic field, it is splitting up into 2 energy levels with the spins aligned to the magnetic field in the lower energy and those opposed to the magnetic field in the higher energy. And we have also seen that the population difference between these 2 levels, N, is N0, that is the equilibrium population difference, into 1 minus 2 exponential minus T, that is the time at which we are looking at the population difference, divided by T1, that is the relaxation time. So now suppose your sweep rate, that is the rate that it takes for the magnetic field to go through the entire sample once, is 1 Hertz per the sweep rate means that is the instrument is sweeping through the frequency and it covers 1 Hertz in 1 second. So to cover 1000 Hertz, it will take 16 minutes. So to get one particular spectra, you will get 16 minutes, which is very time consuming. So this is a very time consuming process. where you take 16 minutes to get one particular spectra. Now, another formula is the signal by noise ratio. This is defined. So suppose this is a signal, this is the main signal, and this baseline, whatever discrepancy is there, that is called the noise. So signal to noise ratio is defined by the peak height above a mean noise level. So we have taken this line, this is the mean noise level, and the peak height above it is the S, divided by maximum peak minus peak separation in noise. So this is what has been taken as the noise, that is the maximum noise minus the peak separation into 2.5. This signal to noise ratio is directly proportional to number of sweeps. So if we just saw that to sweep the spectra once, we need 16 minutes. But if we do it just once, there can be a lot of noise. To improve the signal noise ratio, suppose by 10 times, we need 100 sweeps. So we need to sweep the entire frequency range 100 times, and one sweep was taking 16 minutes. So we need 1600 minutes to get a good signal noise. And that is a huge amount of time. We cannot use that much time for one spectra. Other than that, this is the continuous wave spectra that we are talking about. Other point is that if we are taking 1600 minutes, the sample may not be stable for that long, or the spectrometer may not be able to maintain a uniform magnetic field for that long. Other than that, high concentration of the sample may be required to get a good intensity. And hence, because these low abundance nuclei, they will have problems because that abundance is low, so they will need even higher concentration. So the more refined form of NMR that is used is known as Fourier transform NMR or FT-NMR. There, what we do is that we add an RF pulse for only a short time of few microseconds. So it is represented like this. This red kind of rectangle you can see, that represents a radio frequency pulse. The radio frequency pulse is actually like this wave. It is just represented like this here, which is being applied for a time tau. When you do Fourier transform of this, you can see that this pulse is used to excite the sample, and then the signal of the sample undergoes Fourier transform to get the spectra that we normally get. Here what happens is that, suppose tau is, so what is Fourier transform? Fourier transform is changing the time axis to a frequency axis. So if time is tau, the frequency will be 1 by tau. So if we are applying the pulse for 10 microsecond, the frequency is 10 microsecond is 10 into micro is 10 to the power minus 6. So 10 to the power minus 5 seconds. 1 by tau will be 10 to the power 5 second inverse. That is 100 kilohertz. So a wide range of frequency is scanned. 100 kilohertz of frequency is scanned by just applying the RF pulse for a short time of 10 microseconds. So you are here, what was happening? You are scanning frequency 1 hertz per second. Here what you are doing, you are applying an RF pulse for 10 microsecond, and this is helping you scan 100 kilohertz of frequency at the same time. So when this happens, you are then it follows the normal NMR pattern, where you are exciting 100 kilohertz of frequency. You're following the normal NMR pattern where you're exciting 100 kilohertz of frequency at the same time. And then, so all the magnetization, if you remember, it was in the Z axis. Exciting it is bringing it down to the XY plane. And here there is a detector which is detecting the signal. The signal will come as a large number of superimposing peaks like this, where again Fourier transform is applied. And using Fourier transform, you will get the NMR signal that we normally see. Here, so this basically, you can see that signal to noise, it will be much higher. For example, it is shown for one particular molecule here. The upper spectra is the spectra obtained by Fourier transform, and the lower spectra is the spectra for continuous wave. Continuous wave is the one where we were scanning frequency 1 hertz per second. So it was taking 16 minutes to sweep 1000 hertz. There the spectra is very much noise. It is mostly noise. You cannot figure out which are the spectra of the sample. But in Fourier transform, since you need only 10 microseconds to scan 100 kilohertz, you can do this scan many number of times. So you can see that 500 times you can do the scan in just 1 second. So that will improve the signal to noise ratio greatly without taking too much time. In continuous wave, we were seeing to improve signal to noise by 10 times, we were needing 1600 minutes. And here we are doing 500 scans. So root of 500 will be 10 root 5. So this also just assume instead of 500, we had 100. Then here to improve by 10 times the signal to noise, you are just needing 1 second. Because 10 microsecond itself is enough to scan a large range of frequency. So here Fourier transforms gives much better resolution in the peaks. And so the peaks of the less abundant nuclei like 13C and 15N can be done by Fourier transform. And low concentration is also enough because you can repeat the experiment multiple times. Each experiment is taking much lower time, so you can repeat as many times as you need to get a better signal to noise. So low concentration is also enough. And if you have some very unstable molecules which do not live for very long, then you can study by Fourier transform since it's a very quick experiment. So now we will look at the Fourier transform spectrometer. Here basically what happens is that at the middle of the spectrometer there is a bore. The sample is inserted into this bore in a tube. Then around this bore there is liquid helium. Liquid helium is you can bring it to very low temperatures around 6 Kelvin where the resistance goes to 0. When the resistance is 0, the wire here that is supplying the electromagnetic field, it becomes superconducting. So using this superconducting magnet, the external field B0 is applied. And how the magnet is made superconducting is by keeping it in a helium atmosphere where the temperature can be brought to 6 Kelvin. Now, if you keep it in helium, without any other protection, the heat can be lost very easily. And to maintain the 6 Kelvin also becomes very difficult. So a heat shield is kept around the helium, which is made of nitrogen. This liquid nitrogen heat shield of around 77 Kelvin, it protects the helium from losing too much heat and acts as a heat shield. And since liquid nitrogen is much cheaper than liquid helium, it is used as a heat shield. And further, there is a vacuum chamber to reduce the heat flow even further. So this is how the inside of the spectrometer looks like. And you can see, so the sample is kept in this bore. The magnetic field is applied to the sample. So you have the RF radio frequency transmitter that is applying the magnetic field. And then it produces the signal which is received, and then the data is processed and you get the final spectra. There are some other components also, like a field frequency lock that is controlling the magnetic field. So you can apply magnetic fields of different strengths. There is a shim system which maintains the field to be homogeneous. So if the field becomes inhomogeneous, then you can have spectral broadening, and so this maintains the homogeneity of the field. So this is the very basic principle of the NMR spectrometer. Now, there is one problem that we have to address, that is solvent suppression. What is that? Suppose we have a sample in water for which we are recording the 1H spectrum. The concentration of 1H in water is very, very high because every molecule has 2 hydrogens. So if that is 110 molar, then concentration of 1H in the sample is much lower. It is only like 1 millimolar or 10 to the power minus 3 molar. So the ratio of the water sample to the ratio of the signal of water to the signal of the sample is very high. Means that water will appear as a huge peak and all the samples will appear just as noise. So the sample signal is getting lost, and we have to devise techniques to suppress this strong signal of the water so that the solvent signals can be observed. One of the technique is called pre-saturation. Here what is happening, that normally we apply a pulse. Normally you have your radio frequency in the z-axis. You apply a 90-degree pulse, that is the radio frequency you apply to it, and it comes in the xy plane. But before doing this, a soft radio frequency is applied on the solvent signal. So this is a very specialized radio frequency that is exciting only the solvent protons and saturates their signal. What does this mean? So in water also the hydrogens will have 2 energy levels, alpha and beta. And we know alpha and beta has different populations. Suppose alpha has 3, alpha has 2, beta, alpha has 3, beta has 1. They have different populations. And because of this population, the signal of water is observed. Now this blue region that is shown here, this is a special radio frequency that is applied only on the solvent. It will excite the solvent protons and saturate the signal. It will saturation basically means the number of nuclei in the upper and lower level become equal. So it will excite some nuclei from the lower level to the upper level, ensuring that the number in the upper and lower level are equal. What this will do is that this will completely remove the signal of the solvent, because we know that when upper and lower level are equal, it is called saturation, and in that case no solvent signal will be observed. After doing this, the rest of the process is done, where the sample is excited with the general radio frequency that we use. The sample signal is brought down to the xy plane and then it is detected. So before detecting the sample signal, basically this saturation process is done only on the solvent so that the signal of the solvent can be removed and we can focus on the signal of the sample. Another method of doing this is called inversion recovery. Here what happens is that initially a 180-degree pulse is applied. What this means is that initially both your water and sample magnetization was in the z-axis. When you're applying the 180-degree pulse, the direction of magnetization changes by 180 degree. So just imagine water is the red signal, sample is the green signal. From plus z, they are coming to minus z because of this 180-degree pulse. Now slowly, we know that whenever we give a pulse and the direction is changed, they will always try to go back to the original direction. So you are giving a time tau for the spin to go back to the original direction. And here what is happening is that the time that it takes, T1, for the relaxation is different for water and the sample. So by the time the signal of water has become 0, signal of sample has already become 0 and now is in the upward direction. So in this particular case, signal of water is completely gone and you only have signal of the signal of the sample. Now, if you do a normal NMR experiment where you apply a pulse to the sample signal, bring it down to the XY plane, so it will be somewhere here, and then you detect it. That will give you the spectra, and the water signal will be removed. This technique depends on one criteria, that is, uh, you basically need the sample and water relaxation times to be different. It has to be such that the water, suppose it is like the sample is still slowly recovering, but the water has already gone to plus Z. Then this method will not work. So this method can only be used when they have very distinct values of relaxation of T1. Because if this is not zero, both will come to zero at the same time. So both signals will be lost. You basically need the water signal to come to zero, but you need the sample signal to be in the plus Z so that it can be brought down to XY by the 90-degree pulse and it can be recorded. Now we will look at some other questions based on the principles we just discussed. The decay in NMR signal is due to what? So here the answer is spin-spin relaxation. If you remember, spin-spin relaxation was when the signal that was initially in plus Z is brought to the XY plane and then you give it some time. Along with passage of the time, the XY component decreases and Z component increases till finally the signal is completely in the Z direction. So when the signal is completely in the Z direction, the signal is completely gone. So because the detector is in the XY plane, initially you are getting the highest signal, and after some time, when there is no XY component, the signal becomes zero. So the signal is decaying, and this process is the spin-spin relaxation time. So the decay is due to spin-spin relaxation, option A. Next question is asking, more the shielding effect, what happens to the chemical shift? Here the answer is A. So we have seen that when an external magnetic field is applied, it induces a magnetic field in the electron cloud surrounding the nucleus, and the induced magnetic field will be in the opposite direction to the applied magnetic field. Now, when there is a low electron density, the induced magnetic field is low. So the net magnetic field experience will be B0, that is applied, minus Bi, that is induced. So if there is low electron density, Bi is low, so it is experiencing a high magnetic field. And if electron density is high, Bi is high and it is experiencing a weak magnetic field. Now, how the chemical shift is calculated? Spectrometer frequency is same in both these cases, and you are taking the difference in the frequency of the nucleus you are observing and the reference. Reference is also same in both the cases. So mainly we have to look into the frequency of the nucleus that we are observing. So we know that in the presence of a magnetic field, it splits into two energy levels. And the difference between the energy levels you can write as h nu. So this nu is what we are observing here. When there is a weak magnetic field, the splitting will be lowered. So nu will be less. So in a weak magnetic field, if nu is less, that means delta is less. So it is in less values of delta, that is, it is upfield shifted, or it is called shielded. So in this situation where there is a high electron density around the nucleus, it is called upfield shifted because it is towards zero, or shielded. You can see it is shielded. Or if you have few electrons around the nucleus, then the splitting is high, that is nu is high. If nu is high, delta will be high. So it will be at higher values of delta, which is called downfield shifted or de-shielded. So if we look at the question, more the shielding effect, that is this case, lower is the chemical shift. So this case, lower chemical shift, upfield shifted, or it is called shielded. Next question is asking, in an NMR experiment, the radio frequency is oriented in which direction? So here the answer is at 90 degree to the main field. So if you remember, suppose the field is in the Z direction, wait, radio frequency and field orientation is basically what we are looking at right now. Radio frequency here is, so when we say the main field, we mean the field that the nuclei are experiencing. So the field that the nuclei are experiencing are in the transverse field. We know that because in the transverse field is where we keep the detector or receiver. So the main field is in the XY plane, and we know that the radio frequency B0 is applied in the Z axis. So there is a 90 degree between the main field experienced by the nuclei in the transverse plane and the field that is B0 radio frequency applied in the Z axis. So there is a 90 degree between them. And so it is oriented at 90 degree to the main field, that is option B. The next question is asking, the frequency range of chemical shifts of a proton in a 500 megahertz spectrometer is about how much? So here, for the answer, you have to remember the formula of the chemical shift, that is nu I, the frequency of the nucleus we are observing, minus nu r, which is the reference frequency, by nu zero, the spectrometer frequency. So we know the spectrometer frequency nu zero is 500 megahertz. We have put that in place of nu zero, and delta nu, which we are defining as nu I minus nu r, we are calling this as delta nu. Delta nu is this chemical shift delta into 500 megahertz divided by 10 to the power 6. We assume that the delta range, we are assuming it 10 hertz. Proton scales can range from 0 to around 12, 13. We are just assuming delta around 10. You can take any other value. We are just taking 10 because you can see all the options, they are in like 5, 10 multiples. So we are assuming delta as 10. So the delta nu will become 10 into, once you cancel these and you write it out properly, this much megahertz, which turns out to be, when you multiply megahertz with 10 to the power minus 3, it will become kilohertz. So the final uh, answer, the delta nu, is 5 kilohertz. So we were asking for the frequency range of chemical shift. That is why we are taking delta nu, because we want the entire frequency range. We know the frequency of the reference is at 0, and we are taking the observed frequency. So that is the entire frequency range. So that delta nu is what we have to calculate, and it is coming around 5 kilohertz. You can see the only option in that range is C. Instead of 10, if you had taken any other value, it would also have fallen within this option. So your correct answer is option C. Next question is asking about T1 relaxation. What does it refer to? So here the answer is spin lattice relaxation. So T2 is spin-spin relaxation. T1 is spin lattice relaxation. Just to recap about spin lattice relaxation, we know that in the presence of an external magnetic field, if I is half, the energy levels split up into two, a lower and a upper level. And they will have different populations. Lower will have slightly higher population. Now, when you excite the nuclei in the lower level, they will get promoted to upper level. Or when the nuclei in the upper level are coming down, so suppose you have a nuclei in the lower level, you are supplying energy, it is getting promoted to the upper level. Where will this energy come from? It generally comes from the lattice, that is everything that is around the nuclei that we are observing. Or if a nucleus from the upper level is relaxing to a lower level, then it is releasing some energy, and this is also being absorbed by the lattice. So the lattice is responsible for different population adjustments. So if you're suddenly perturbing the population with a radio frequency, it will tend to come back to the equilibrium population. And it will do that either by releasing some energy into the lattice or taking some energy from the lattice. And this is called spin lattice relaxation or coupling. And this is T1. So T1 is option B, that is spin lattice relaxation. T2 is actually option C, that is spin-spin relaxation, if the question was T2. The next question is asking, for a nucleus with spin 3 by 2, what is the number of allowed transitions? So here, let us look at, so if I is 3 by 2, we know m is minus I to plus I in increments of 1. So m will be 3 by 2, half, minus half, 3 by 2. These are the four m's. And the selection rule tells us that single quantum transitions are allowed. That is, m can change by plus minus 1. So you can have 3 by 2 to half, half to minus half to minus 3 by 2. Note that up and down transition is considered a single transition. So these are the three transitions allowed with delta m plus minus 1. So the correct answer is 3. That is, the number of allowed transitions in a nucleus with spin 3 by 2 is 3. The next question is asking, in an NMR spectrum, which factors will contribute to the line width? Just 1 second. Sorry, I guess I showed. But anyway, I'll just discuss the answer. So if you remember, there are two main causes of spectral line broadening. One is from the Heisenberg's uncertainty principle, where every energy level there is a certain uncertainty. So it does not have a single value of energy. It can have multiple closed values of energies, both the upper and lower levels. So instead of a single peak, which would correspond to a single wavelength, you will get a certain range of wavelength, which results in this spectral line broadening. And the other reason is the field inhomogeneity. Due to, so no machine is ideal or perfect. Due to some aberrations in the machine, that the field can be inhomogeneous in some places, and that will result in if different nuclei get are experiencing a different magnetic field, that will also lead to a spectral line broadening. So which factors are contributing to this spectral line broadening? Magnetic field inhomogeneity, yes, it is one of the factors. Spin relaxation or spin lattice relaxation, these are all, how do these contribute? So basically, when I was discussing this, the point that I did not put too much stress on was the lifetime. The Heisenberg's uncertainty principle is delta E into delta T, where delta E is the uncertainty in energy and delta T is the lifetime of the spin in that state. If the lifetime is altered, that will affect the delta E, that is uncertainty in energy, and that will increase the line width. So how the lifetime can be altered? It can be altered either by spin-spin relaxation. We know that in spin-spin relaxation, the signal decays. So the lifetime in that particular state is altered. Or spin lattice relaxation, a nuclei in the upper state can release energy into the lattice and come down to the lower state. So again, the lifetime in the upper state will be altered. So both by spin-spin relaxation and spin lattice relaxation, the lifetime in a particular state, that is delta T, is altered. If delta T is altered, in order to maintain the product as constant, delta E must also be altered. And if delta E is altered, then the spectral line will broaden even more. So all of the above contribute to this spectral line broadening. So this is all about class 1. I have covered the basic principles of NMR, discussed chemical shifts, spin-spin coupling, intensities of the signals, and so on, different factors. I've discussed a little bit of the instrumentation, and basic principles of NMR. So this class has been recorded and I will upload it. So you can go through it, and if you have any doubts, you can come back to me with the doubts in the next class. I'll end the class here, and as I said, the videos will be uploaded.